Alright, so we're going to go ahead and start a new unit on an introduction to derivatives and rates of change. This unit is probably one of the most important units when we get into calculus. It's basically the start of absolutely everything calculus related. Okay, so what it says is, as students of life and algebra, you've studied many rates of change for different situations. How fast we drive, how our savings grow over time, the rate that the world population changes, unemployment rates, and so much more. In each of these studies, we can express one variable in terms of another. That is, as a function, y equals f of x. We have been studying the change of y as x changes. So the rate of change of y with respect to x, which we can write like this. We can write change in y over change in x. All right. And then another way of writing that, which looks actually very calculus related, is delta y over delta x. This delta really just means change. It stands for change. All right, so you have your change in y and your change in x, which I think most of us have probably seen before. I'm hoping that you recognize this as something like slope. Okay? And it says if x changes from a to b, then y changes from f of a to f of b. So instead of what we wrote above, our change in y and our change in x actually look a little more like this. So it's going to go f of b minus f of a over b minus a. Alright, so remember f of b is just the y value when you plug in b, and f of a is just the a or the y value when you plug in a. So for this fraction right here, the order doesn't matter. As long as you're consistent. So if you put b's in front, top, and bottom, that's good. Or a's in front, top, and bottom, then that's also good. So as long as you're consistent. Okay? Let's check and make sure there's nothing else. All right. So what we have here is it talks about average speed. So it says the total distance traveled d divided by the elapsed time period t. So graphically, the average speed is the slope of the secant line. So something that's really important is this word secant. You learned it in geometry, which was like, I don't know, a million years ago. So when you have a secant line is a line that touches the curve two times. So it touches two times. I always remember because secant has an s in it, and I say that it goes through a second time. Okay? So if we have any old function, so I'll go through and just draw a random one. Alright? And it asks me to talk about my average rate of change. Okay, my average rate of change. I could draw a secant line to find it. So I could draw a dot right here. I could draw a dot right here and ask for the average. Actually, let me fix just a little bit to make sure that it only goes through twice. I'm going to pick here and here. Technically, I'm okay either way, but I want to make it very clear for you guys that it should touch twice. Okay? So, and then we would have this one as A, and this one as B. Okay? So, what we have analytically is that the average speed is the absolute value of the distance over time. We use absolute value because speed is always going to be positive. Okay? So what you have is this acronym right here, AROC. AROC, which stands for average rate of change. And the average rate of change is really just equivalent to the slope of the secant line. Okay? Alright, and we said secant is defined right there. Okay? Now what we can also have is what's called a the instantaneous speed, or the speed at a specific instant in time. Graphically, the instantaneous speed is the slope of the tangent line. So this one is different. Secant goes through twice. Tangent touches, it's a line that touches the function exactly once. Okay, so it's a line that touches the function exactly once, or one time. So what we have is we have a graph. So if I have this graph right here, almost identical to the one I had before, and I'm talking about doing the tangent line, I could do the tangent line at this point, okay? And I'm just picking a random spot to draw it from, and you would have it right here, and it would just touch this function right here, okay? So it says analytically we need calculus to determine the instantaneous speed, so that's what we're going to be learning, how to do the instant rate of change. And we have our saying right here, or our acronym, instant rate of change. Instant rate of change. Okay? Which is just the slope of the tangent line, or the one that just touches. Okay? Alright, so now let's look here. We have an example. So it says, after a person exercises, their rapid heart rate decreases as time passes. It says, let h of t represent your heart rate. It says, write an expression for the rate of change of your heart rate over the period from 0 to 90. So what we're going to do is we're going to use what we wrote above. So just as a reminder, above it said delta y over delta x equals f of b minus f of a all over b minus a. So we're going to apply that here. Okay, so go ahead and pause, and then you can do. So all we're doing is h of 90 minus h of 0 over 90 minus 0. It's really just the slope. If you wanted to simplify this, it would just say h of 90 minus h of 0 over 90. Now we don't have the function to actually plug in, but this is an expression that would tell you how it changes. So it says write an expression. We have an expression, so we've done exactly what they've asked us to do. Okay? Now for the next one, it says a roller coaster has its largest drop modeled by the equation below, where d of t is measured in feet, time is measured t in seconds, and it gives us an equation. So it says find the average speed of the roller coaster from 2 to 8. So this should be the same exact thing. The only frustration is that you have to go through and plug in the numbers. But if you use Desmos, I'll teach you how to use a table in Desmos. So give me just 1 second. Alright, so it doesn't look like I can get Desmos up, but what I'll do is I'll explain to you how it works. So what we can do is we can do the average speed of the roller coaster, that's change in distance over change in time. So we'll do d of 8 minus d of 2 all over 8 minus 2. Now, what I was saying is the only frustration is plugging 8 into this function is a very long process. So what you can do instead is if you go through and you put it in your calculator, okay, so if you put it, or actually let's not do calculator, let's use Desmos. If you put it into Desmos, this function goes into Desmos, okay, so once you've put it in Desmos and graphed it, use x's instead of t's, so go ahead and do that. You're going to press the little gear button and it'll allow you to see a table. Once you do that, you get to plug in any number that you want to that function. So let me pull it up on my phone. Go ahead and input it. Alright, so I'm ready to go ahead and input any values that it wants. So it wants 8, so I'm going to plug in 8. So 8 is 671.36, so we're going to write 671.36. And then we're going to subtract d of 2, which is 290.54. And then on the bottom, we'll have over 6. Okay, and that gets us 63.47. And then we want to make sure that we're using units, so it looks like it's feet per second. And we're going to want to make sure we use units every single time we're asked a question. That way we know if our answer even makes any sense at all. Okay? Now it asks us the same thing, so find the average speed. So I'm going to do the same exact thing, delta D over delta T, change in distance over time, because speed is distance over time. We're going to do D of 6 minus D of 4 over 6 minus 4. Oops, that got squiggly. Okay? So again, I'm just going to plug it into my table, and I can do the same thing with my TI Nspire if I want to use that instead. You just go to the table by using Control T. So this is 470.18 minus, and then we need 4, which is 373.16. And that's all over 2. Okay? And it looks like, and I should have been using these squiggles to just tell you that it is an approximation, but it's 48.51 feet per second. So the only difficult part about this is really just knowing that the plugging in part is really not the part that we're trying to focus on, but it is something that's integral to getting the answer right here. Alright, so now we have one that's the traffic flow at a particular intersection is modeled after the function f. So really it's just giving us a whole new function. This one just looks kind of scary, that's all. So it asks us to find f of t for t equals 8. What that really just means is we're going to plug in 8. So f of 8 equals 92 plus 5 sine 8 over 2. Wow, that's squiggly. What the heck? Over 2. So I'm going to plug into my calculator 92 plus 5 sine of 4. And I'm going to plug that straight into my calculator because why not? Make sure it's in radians. And it's approximately 88.216. And that's going to be f of t. So it's the traffic flow. So 88 cars, I guess. Okay. Now, it asks us in the next part to make a sketch of your graph. And I bet you, most of you are looking at me like, that's insanity. We don't know what that looks like. So all I'm asking is that you know that sine does a bunch of waves. Do you know that sine is a bunch of waves? Yes? Oh, good. That's great. That's all I need. So what I want you to do is I want you to draw one that has a bunch of waves. Oh, gosh, this is horrible. Pretty close. And we want to label it. So T is for time. And these are the cars, or the number of cars. Okay? Now it says, what is your average rate of change of the traffic flow over the time interval from t, or from 10 is less than or equal to t, which is less than or equal to 15. So from 10 to 15. So we're going to do the same exact thing, and we were using f, so delta f over delta t is f of 15 minus f of 10 over 15 minus 10. Now what we're going to do is we're going to go through, and I'm going to put this in my Desmos again, or you can use your TI Nspire, that's fine too. But at home, it's much easier for me because I don't have a TI Nspire at home, I'm not that fancy. So I can just plug this in to my Desmos. Now remember, you have to use X on Desmos, okay? So what we can do is make sure that we're graphing in radians. Okay, great. And we can go to the table. Then it gives us our values. So f of 15. So I need to plug in 15. And if I plug in 15, I get 96.69. Then I plug in 10. And it's 87.21. And it's all over 5. Okay? So I'm going to make sure that I put that in the calculator. That way, if any of my rounding changes the answer from my answer key, minus over 5. So that gives me 1.896. And that's going to be cars per minute. And as long as you're close to there, any rounding errors, as long as you're within like a thousandth, so if it was 1.897, 1.898, then you're fine. Okay? Now it's asking you to estimate the instantaneous rate of change of traffic flow at t equals 8 by finding the average rates from 8 to 8.1, 8 to 8.01, 8 to 8.001. So this is actually a lot like what we were doing with our limits by tables. You're just basically taking your secant line and you're trying to get it closer and closer and closer together so that you're estimating the actual tangent line. Because the closer that your two dots get to each other, the closer you are to being exactly one dot. Okay? So what we're going to do is we're going to do f of 8.1 minus f of 8 over 8.1 minus 8. And then over here, I'll do f of 8.01 minus f of 8 over 8.01 minus 8. And then I'll do the last one, f of 8.001 minus f of 8. And then I'm going to pause it, and you should pause it as well so we don't waste each other's time. And we're going to put that in the calculator, okay? Alright, so I went through and I got my slopes, or my instantaneous rate of change. So what we're looking at is it goes from negative 1.6 to negative 2.03, and then when we get even closer, it gets to negative 10. So we'd have to continue going closer. This is almost like doing limits by tables to know exactly what we would get at our instant of 8. Okay? So now what we're going to go through is we're going to talk about find the average rate of change over the 2.5 hours. So since it's asking us about 2.5 hours, you want to look at the beginning and the end. We're doing the secant line for the beginning and the end. So what you really need is you need f of 150 minus f of 0 over 150 minus 0. Which gets you 1/5. Okay? And that would be 1/5 in our distance, it looks like, per minute, miles per minute. Or you could say 0.2 miles per minute. Okay? Now I know we don't usually talk in miles per minute, so if you wanted to convert that to miles per hour, you could. We'll do that later, but I'll show you now. So we have 0.2 miles for 1 minute, or we could keep it as 1/5. Let's do that. That'll be easier. So 1/5 would be 1 mile, 5 minutes, and there are 60 minutes in 1 hour. So when you go to do this, you just cancel out your minutes, and you have miles per hour, which gives us 12 miles per hour. Not very quick. Okay? So now we're going to go through and we're going to talk about how fast is the car going between 30 and 50 minutes. So 30 and 50. So we need to look at those. So 30 and 50. If you notice, between 30 and 50 is a flat line. So we are stopped. Not going anywhere. Okay, now let's look at the next question. It says, when is the car traveling the fastest? So, fastest means we're looking for the fastest change of distance per time. So what we're looking for really is just what is the biggest slope? And technically we should put it in absolute value bars, because it doesn't matter this one we're talking about, so going down we could still talk about that being the fastest. Okay, so we're really looking for slope. So you want the biggest slope. So it looks like it's from 0 to 30. From t equals 0 to t equals 30. And it looks identical from 50 to 80. Okay? It says, when is the car traveling the slowest? So I'm actually going to write in here, let's ignore the parts where we're stopped, because we're not really moving at all then. Okay, so ignore when stopped. So if we do just the slowest, that would actually be from 100 to 150. Because that slope is the least steep. Now, the question that we have is, why is the segment between 100 minutes and 150 minutes negative? How could that happen? Well, at 100 minutes we've traveled 40 miles, whereas at 150 minutes we've traveled 30 miles. So what's happening? Yeah, we're going to go back. We're going back. Oops. Going back home, or back to where we started. Okay, or turning around. It says, what is the speed of the car at 20 minutes? So remember, speed is really just talking about our slope. So what is the slope at 20 minutes? I would count mine as rise over run. So rise over run. So it's up 20. Oops. And over 30. So we have 2 miles per 3 minutes. And if we want to make sure that we know what that's like in actual speed, or not actual, but what we usually measure, 60 minutes in 1 hour, that gives us 120. That gives us 120 over 3, which is 40 miles per hour. Okay, so now they ask us, what is the speed of the car at 70 minutes? So if you look at the graph, at 70 minutes, the slope is actually identical to what we just did. So I'm going to write C above. For work, then I'm going to write that it's 40 miles per hour. Okay? Now, let's talk about this Ferris wheel. So it says, you've been waiting in line for 15 minutes to ride a Ferris wheel at National Harbor. It took 10 minutes to ride to the top and 10 minutes to return to landing level, which is near ground level. It says, graph the function as described. So what I'm thinking is 15 minutes in, I'm still on the ground. Okay? Or at, near ground level, landing level. Okay? Then I get to ride to the top. Okay? And that takes me 10 minutes. So we're at 25 minutes. And then I get to ride back down to the bottom. And I get to the bottom 10 minutes later, which is 35 minutes. And this, they didn't tell me what the height is, but I'm just going to put that this is the top. Okay? So what it says now is it says, how could you find the speed of your ride? It's difficult to calculate the rate of change of distance with respect to time at any given instant in time if you don't have a type of measuring device when the function is a curve. So before, we were just looking at straight lines and we could just do the slope. But how can we find the speed at these ones? This looks definitely much more difficult. So what we're going to do now is it says, suppose an object is projected from the top of a 112-foot building and its path in seconds is defined by. Now, one thing that's really nice about this example is that we actually have a table where we can find the average speed. So I don't actually have to plug this one in. I can just find it right here in my table. So we're doing the same exact thing. So we're going to do f of 2.2 minus f of 1.8. And it's going to all go over 2.2 minus 1.8. Okay, and then I'm going to plug in my values from that table. So plug in the values from that table, and then I'm just going to write the final answer. So pause for just a second so you can plug those tables in, or those numbers in. Okay? Alright? So once we've done that, let me see my answer key, is it gets us, once we simplify, it gets us 12.8 over 0.4, which is equal to 32 feet per second. Okay? And then we're going to go through and do the same exact idea for letter B. So we're still doing change in distance over change in time. And we're going to do f of 2.03 minus f of 1.97 all over 2.03 minus 1.97. Okay? And that's going to get us approximately 32 feet per second. Okay? So what it says is, it says when the line through the points 1.97 and 2.03 is drawn together, the straight line has now become an approximation of the curve. The slope of the line shows at the rate of change at 2. So basically what it's doing is it's giving us a rate of change, and it says if we choose any point on the graph and zoom in really close, it will appear to be a straight line, also known as the tangent line. So we're going to be learning about tangent lines. Okay? Alright, I hope this helps.